Hello, everyone. Welcome. Thanks for coming to my talk today. This is Vibing with Data. I'm Andreas Kollegger, ABK of Neo4j. And this is going to be really a talk in two parts. I'm going to introduce the idea of knowledge graphs and what a graph is. And then we're going to get into the fun part, which is how you'd go about building a multi-agent system to work with graphs, or really you can take the same approach for working with any data, so you can get to the point where you are vibing with data the same way you can vibe with code. So let's get into it. We're going to start with the easy part, which is what is a knowledge graph? And I know that this is the main stage, but if I can get a quick show from the audience, people who have used graphs before? I can see some hands. Okay, so some of this is going to be redundant for some of you, and you can go ahead and go down on social media for a minute while we cover this part. This is my favorite thing about graphs. I talk to a lot of people about graphs all the time. I talk to people who aren't using graphs yet. And for many people, graphs end up being on their roadmap. There's something that they're going to eventually do. They think, particularly with Gen AI and with doing RAG systems, they know that graph RAG sounds really great, but they'll do that maybe tomorrow. But graphs are inevitable. Everybody eventually will realize that this is what they need to be doing with their data, particularly if you're working with Gen AI or if you're working with agents. So let's step back for a second, and I'm going to guess that I'm not going to ask for a show of hands here. I'm going to just assume everybody in the audience at some point has built a relational database. You've designed a bunch of tables. And I'm going to say that probably 99.9% of the relational databases in the world somewhere have a join table. So let's start with join tables. If you had a person table and some product table and this product person table and person product table in the middle, you've got a join table, right? What if you were building a RAG application and you want to answer a question like, well, hey, what products has this person purchased? Let's say there's ABK here, he's signed into your app. You want to figure out what is ABK purchased. How do you do that with a relational database? Everything starts with a join. From the person table to the person product join table, you can find out the pairs there. And then from that over to the product table to figure out that he's bought a chair, a lamp, and a desk. Fantastic. Easy question to answer. What if you want to extend that question a little bit because, of course, you're running an e-commerce site, let's say. So who else bought those products? Good question to ask. How do you do that with the relational database? You got over to the product table. You can just use joins for getting your way back. Join back from the products that you have already found, select back to the person product table, and then from that, all the way back to the person table. Now here I'm just showing one person, but of course this could be many people who have bought those same set of products. Now you've got all the way from the person table to the products and back to other people who have bought those products. You could ask another follow-up question, going back to ABK, who's the user logged in. So given that you know what he's purchased and what other people have bought that, you could naturally ask, what products should I recommend to ABK to buy next? If you're doing this relational database, you would, of course, join again, and you would, wait, okay. It's getting a little confusing. There's too many joins. It's a little hard to think about. You can do this yourself, but if you imagine trying to do this with a RAG application, like you have a natural language question that you want to easily map to SQL to answer this, pretty hard to do. Obviously, I'm going to redraw this as a graph. To do that, we're going to start by getting rid of all the gray boxes, all the records that weren't part of the original query. But really, this is just to help us think about what does the mental model actually look like. So we still have the same records that were selected through the relational database. We've got ABK, EE on this one side, the chairs, the lamp, and the desks. Fantastic. But now, for all the join table records, in a graph, you just replace those with actual data records that are called relationships. And relationships, of course, connect two different things together. How are these two things related? So we've got ABK, who's a person who's purchased some products. We've got EE, who's a person who also purchased some products. Same data representation, just in a different format. Now it's represented as a graph. If you rearrange that a little bit, it becomes even easier to see how to ask these questions. Now, starting with ABK on the left, EE's on the right-hand side, and that he's got one little dangly product that ABK does not have a connection to. With this kind of rearranged drawing, it's the same data, just rearranged. Let's ask those same questions and think about them in terms of what would that look if you were doing pattern matching. So easy patterns. Neo4j is a graph database. As a graph database, we have a query language called Cypher. It's inspired by SQL, but it adds this notion of being able to do pattern matching across data records. So if you ask what products did ABK purchase, you describe a pattern that goes from ABK through purchased relationships to whatever products he's purchased. There's a match clause for actually doing that pattern matching, so you match that pattern, and then return the ABK products, which is the end part of the pattern, return that as the result. Easy peasy. Who else bought those products? You just extend the pattern from ABK to his products to other people that bought that product. Still a pattern match. Return those other people. What should ABK buy next? Extend the pattern a little bit more from ABK to ABK's products to the other people to the products that they purchased, but now you add a predicate for a negative pattern match. You want to say where ABK has not purchased those products. Now you can answer the question, what should ABK buy next? You want to find out what other people have purchased that he has not purchased. Go ahead and find that. It ends up being a very simple pattern match. This is the basics of actually having a knowledge graph. A knowledge graph is kind of a database that represents information as nodes. So all the data records are pretty much turned into nodes. Those are people, places, and things. And all the join tables you might have had in a relational database, those turn into relationships. Also the foreign key relationships, those also of course turn into relationships. So there's almost a nice one-to-one mapping from a relational database model to a graph database model. The difference ends up being in the kinds of queries you could run and how efficiently you can run them, and also of course for GenAI, how nicely those map to natural language questions. So you've got nodes, relationships, the data records that those represent can have arbitrary key value pairs, so you can have people with names, birth dates, all those kinds of things of course. And for the nodes you create, for the data records, we often say that they have this one-to-one correspondence, like we had the person table. If you put that into a graph, you're going to have a label person that you add to that node. But nodes can have multiple labels. So you could have a person who's a customer, who's also an employee, who also is maybe, I don't know, a special person, a VIP as well. All these ends up being sets of the same set of nodes, subsets of the set of nodes that are people, but because you can add multiple labels to the individual record, it's as if the record lives in multiple tables. In a relational database, you'd have to actually probably have that in multiple tables or have some discriminating column that lets you figure out, like, is he an employee, is he a customer, is he anything else? With the graph, you just add more labels. Each label provides a subset of the nodes that have that label. Relationships always have a direction. They don't have multiple labels, they only have a single type, so purchased or likes or friends, those kinds of things. And you do pattern matching for actually querying all of these things. And it turns out, again, to be really nice for doing GenAI because it maps really nicely to natural language. But this begs the question, even if there's a nice one-to-one mapping from relational databases into graphs, and you could just import relational database pretty easily into a graph, if you're not already familiar with particularly graph data modeling and you just think about most relational databases, the way they've been denormalized and they don't actually represent the original domain very nicely, in a graph we prefer to have a very normalized data model that has a very close correspondence with the actual real world. So if you just take any old relational database and turn it into a graph, you'll get a graph, but it may not be the best graph. So it helps to have some understanding about how to do graph data modeling. Now you could either learn that, or as you're learning that, you could build an agent that has incorporated into it all the things you learn, or maybe find agents that exist, for instance, the one that I'm working on that has some of my knowledge about how to do graph data modeling, and just use that for actually doing your data modeling. So I'm going to walk through that. This is the fun part. This is how to build a multi-agent system where the multi-agent system's goal is to build a knowledge graph. So it's an agentic knowledge graph construction tool. Okay. Another somewhat ChatGPT, maybe made up quote, probably you've heard Einstein say this: God does not play dice with agents. So in a multi-agent system, and now actually I'm going to peer out past the lights and ask another question. People who have built agent systems at all? A couple of people start to get into agents. So I'm going to do a very brief, actually I don't think I have a slide on this. I'm going to digress for a moment to talk about just what agents are and the basic idea of actually interacting with an LLM. And then I'll talk through these points here, which is how to go from interacting with an LLM into how do you make a multi-agent system out of all this stuff. So stepping back for a second and thinking about LLMs, you've used probably ChatGPT or Claude, or Gemini to actually just have a conversation, right? And we realized that they're really great at having world knowledge and doing generalized, problem solving on things. They're not so great at doing problem solving on very particular areas of knowledge that you might have that the LLM doesn't have public data to train on. This is the experience I had when I started to work with Claude and even ChatGPT, asking them to build graphs. They're pretty good out of the box for doing small graphs. The more complicated the graphs got, the bigger they got, the harder they had, the worse they were basically at actually creating those graphs, because they didn't have specialized knowledge about actually graph modeling. And what I found out what they were doing is often just mapping the relational thinking directly into doing, okay, here's what a relational database would look like. Let me just make that into a graph. And as I just said, that isn't always the best idea. So probably whatever you're working on, you have similar experiences. Even when you're just coding, with a coding assistant, you realize that for some set of things that are maybe in, coding contest evals and things like that, agents are really good at competition level coding. If you ask them to do, particular algorithms, they've seen those algorithms before, they can basically reproduce those algorithms in the language of your choice. But they may not know a lot about the work that you're doing, and they'll have a harder time actually doing the work that you're doing. That's really the key about actually building a multi-agent system, is it's not just asking an LLM, hey, here's something I want you to do your best job at this. You take the thing you know how to do, and instead of having a single interaction with a single agent, with a single LLM, you wrap the interaction with the LLM into what's called an agent, where an agent is basically a software module that has what's called a system prompt for telling the LLM, I want you to be an expert at Python coding, for instance. You're an expert at Python coding, please answer the user's question. That could be the initial instruction, and then you give the user a question as well. Bundle that all up into the agent, and let the agent actually then repeatedly work with the LLM, asking a question, getting a response back until it thinks that the answer that the user originally asked has been answered. That's better with the diagram, but hopefully that made a little bit of sense. What ends up being true is that all the interactions you have with an LLM can be incorporated into a single module that is called an agent. And as soon as you've got something into a module, we're all software developers. We know once we've got any kind of modularized software, we can put multiple modules together. We can both have composed modules. We can also decompose modules. For really big modules, we know when particular source files get too big, one of the good things to do is go ahead and break that up into multiple sub-modules or sub-functions or sub-files as well, so that it's easier for you to work with the data. The same thing ends up happening when you're working with agentic systems. You might start with an open-ended dynamic conversation with Claude. Once you start to build an agent, you break down all the prompting you were doing, all the, hey, Claude, you got that wrong, think about it this way, and you keep nudging it. All of those nudgings turn into instructions you give to an agent that then you put together with a bunch of other agents, and then all together, they can go ahead and execute on the overall goal. So now I'm going to walk through this particular multi-agent system with the top-level goal of creating a knowledge graph. Okay, so you start with a high-level goal. My high-level goal is I want to construct a knowledge graph. I know how to do that. I know I've had biases about the right way to do that. So I'm going to take my biases about how to think about that, and I'll put my data engineering hat on. And for each of the things I would do as a data engineer, I'm going to encapsulate that into an agent, and then put all those agents together into an overall system that more or less looks like the workflow a data engineer would go through from somebody's asked me to do a job, I want to clarify what they mean, and then, okay, I know what they want to do now, let me go figure out what data is available, figure out the right data to use to answer the question that they've given to me. Then with the files that I know that I've got available, the data sources I have available, I'm going to come up with some sort of a data model, build that, and then once I finally got that data model, I can finally run some analysis or some queries on that. That general flow can turn into exactly a multi-agent system. So that's what I'm going to do. Okay, this is what the system looks like. I'm going to walk through all the boxes, one box at a time, but really this ends up being a single agent, which is the top one, the knowledge graph agent. It's got some sub-agents itself that have specialized areas of focus. And then for each of those, it also has more sub-agents that specialize in particular parts, particular steps within an overall workflow. The thing I want to draw attention to here, a little bit about the color coding, I suppose. All of the colors are agents except for the green bits and the red bit. So the green bits, I should have used yet another color, I guess. You can see there's a knowledge graph way over on that side. Okay, that's the database that we're ultimately going to create. But then on the bottom, the output of these agents, unlike many agentic kind of workflows, you hear this idea about doing tool calling or function calling, where you write some sort of a Python function or JavaScript or Java, whatever else language you might be using, and you let the LLM know what tools are available, and it can call those tools when it thinks it's appropriate. Now, usually those tools take actions. The approach that I have here, being a data engineer, is not to immediately take actions, but first to use the tool calls to construct a plan that a user can then approve before the plan is executed. Particularly when you're doing something like creating a database, you want to work in small batches. You want to figure out, okay, is this the right model to use? Let me try that out. If it's not, I want to do it again. So it ends up being a bit iterative in each of the steps. And so you want to craft the agent itself to be the same way, so that as it's progressing, you don't want it to go off and just do things. You want to check back with the user and say, hey, here's what I think you meant, or here's what I think I should do. Is that correct? And before it even does it, instead of doing it, say, that looks correct, add that to the plan of action that we'll take later on, so that at the end of all of this, if you go from small samples of like 10 files you're doing a data import on, if that happened to work well, you don't want to go through the entire interaction with the agents again to figure out how to import 1 million files or 10 million files. Once you've got a plan that works, that red box at the bottom ends up being just execute the plan. Everything else on this diagram is an agentic workflow for coming up with the plan. This is the kind of vibing with data aspect of this. You're still kind of generating code, but not just open-ended code. You're generating tool calls that have been described inside of a plan. Okay, let me go through each of the little boxes in more detail. The top level agent is responsible for just basically chatting with the user, being friendly, describing what the overall goal is. You can give it some idea about like, okay, you're a knowledge graph, modeling expert, and you want to help the user figure out how to go from an idea to having a knowledge graph you can work with. Underneath, these are the kind of workhorse agents. And I've got 3 specialized agents. The 2 on the left are for doing the data import itself. And then once you've constructed that graph, there's another agent called the GraphRag agent that can take advantage of all the information that was accumulated during the modeling and actually build a GraphRag agent that has different retrieval strategies based on the motivations for building the graph in the first place. As a data engineer, we know this, we hear this all the time. The right way to design any kind of a database is based on how you want to answer user questions. If you don't have user questions, you don't necessarily know how to design the data. Since we're starting with like building the data from motivating from the user goals, if we capture that, that helps us also know what kinds of questions can be answered out of the data, because the user's intention actually describes what the purpose of the data is. So that as a result ends up meaning the GraphRag agent way on the end can know what to do because it knows why the data was created in the first place. Okay, so one specialized agent for a structured data workflow. This is for importing CSV files. Another agent that is very similar, but for doing unstructured data import. Unstructured data follows the same pattern as a workflow, which we'll get into in a minute, but the difference is at the end, the output of that, rather than being a structured data that you create, it's the classic, I've got some text files, I need to chunk them up, and then actually do some vector embedding, that sort of thing. So the unstructured data agent specializes in that, and then the GraphRag agent at the end. So if we go through the individual workflows here, starting with the structured data, and this again is similar to what happens in the unstructured data, everything starts with an agent whose only job is to ideate with the user, to clarify, well, what do you actually want me to do? What kind of data are you interested in? What is the point of actually doing this in the first place? And not just for the sake of like talking, but the output of that talking is also captured inside of the plan, so that part of the plan that gets executed knows the original motivation. So again, all the way to the final product of having a graph and then doing GraphRag on that, the original intent has been captured and can be used all the way through. So then based on the user intent, let's say the user described that they want to do some product analysis or some product recommendations for people and products that we just saw earlier. So okay, you describe that in a little conversational interface, capture that inside of the plan, and then you move on to another sub-agent whose only job is just to look at available data sources, and here it's just restricted to the files that are available. Look at the files that are available in the file system that can be imported, and given what the user wants to do, what files are relevant for people who've bought products. Find those files, suggest those to the user, and say, hey, here's what I found. Does that look okay? Ask the user for approval, and if the user approves, move on to the next agent. The next agent's got a bit harder of a job. It's got to take a look at those CSV files. And probably we've all seen messy CSV files on Kaggle or just like in our own data centers or wherever you work. There's millions and millions of CSV files floating around that people have created for different reasons. Sometimes you can look at a CSV file and immediately know what to do with it. Sometimes it's kind of hard to figure out what the column names are. Maybe there aren't any headers. That's the worst case scenario, of course. The schema proposal agent itself actually has the entire job of like looking through the available files, again with user intent in mind, and figuring out, is all the data here relevant? Which columns do I care about? And then also figuring out, how do these files, if you have multiple files, how do they relate to one another? And so come up with a construction plan for saying, okay, for this people file, I'm going to, let's say, import that and create a bunch of nodes for people. I also have a product file. Okay, that looks pretty simple. I'm going to just go ahead and do a batch import of that as well. So create a rule for doing import of the people and the products. But then you want people and products to be connected somehow. The agent also has to take a look at how to actually do that correlation. Like, we know that probably in those files there are IDs. ID naming can be tricky, but you can ask an LLM to do this. You can give it some actual, a little bit of free leave to just do the analysis on its own. But this is one of the areas where, in addition to letting the LLM showcase how smart it is, you also want to have lots of verification checks. So once it's figured out what the people are, what the products are, and it thinks it knows that here's the person ID and the product ID, and maybe it's got like a person to product ID, maybe it's found another table that, another CSV file that can correlate these things, it'll come up with a plan, it'll offer that to you, but then you have to approve it. Two things will happen actually at that point. A verification step will have happened that is rule-based, that will actually go through, look at the construction plan, and do a sanity check to see that those fields actually exist, that the files actually exist first. Because even at that step, even though you've told it, here's the user intent, and you've told it, here's the files that are available, when it does the construction plan, it still might make up file names. It still might make up column names. At every step, whenever you've got something concrete, you can verify, add verification steps to the agents and to the tooling. With all that verified, you then double check with the user saying, hey, I've looked at this, it looks sane, it looks like it's, satisfies what you want. Is that correct? If so, this whole workflow can be done, and the output ends up being this graph construction plan. In the middle here, this is the unstructured data workflow. It works pretty much the same way. So there is still double checking with the user. Okay, you actually want to add some unstructured data as well. I found some markdown files, let's say, that are here that have been scraped from the web, and maybe there are product reviews or comments and some comment on like Reddit or something. I found relevant things that are saved in Markdown. I can import those if you'd like. And then it gets to this final part, which is the equivalent of the schema proposal. But instead of doing schema proposal at this point, when you have unstructured data and you want to construct a knowledge graph out of that, you don't have CSV files that have tables that you can neatly map into some sort of structure. All you have is open-ended text. So this is where, in kind of a classic RAG sense, you start with looking at the text and chunking it up into like reasonable sized subtexts. And then feature those, you would do a vector embedding. That's all pretty straightforward. But you actually want to connect that into a knowledge graph, or turn that into a knowledge graph that you can connect the unstructured data to your structured data. So how do you do that? Okay, you still go through doing all the chunking, but then you add an extra part of the process, still driven by an agent, where the agent is going to take a look at the text, and it knows what the user's intent was. It also knows from the previous phase, if there is structured data, here's the structured data that exists. It'll see that they're people, it'll see that they're products, whatever else might be there. It can then look at the text, trying to see if it can identify, well, does the text mention products? Does it mention people? Any of the other things that exist in the structured data. The agent can go find that inside of the unstructured data. This is called named entity recognition. So it's named entity recognition with some constraints guided by the structured data that already exists. Those entities, or possible entities, I guess I should say, that seem to appear inside of the text can get pulled out of the text, so you'll have a chunk inside of the graph that is the raw text, but for that chunk, if it mentions ABK, there might be another node that gets created that is the ABK node. Now that node is not necessarily the same ABK as the one that you have in the CSV files. So don't just assume that it's the same, but later on in this process, the agent system will actually try to make some correlation happen. But the initial step is just find the things that exist. Find the people, places, and things that are relevant for the user goal and relevant for the data we already have. Pull those things out, do the named entity recognition, and for all those things that you've pulled out, what are the facts that have been stated? So you can also do fact extraction. And this is, you might have heard the term triples. This is where triples come into play, where a triple is basically like a thing that has a relationship to another thing. So ABK likes coffee, or ABK purchased a chair, I think is what the original graph was, and a desk and something else. So if those things appear inside of the text as well, and like maybe I've posted a review complaining about that the chair always squeaks, and that's good to know, that's good feedback for the manufacturer, let's say. That looks like a good fact that is relevant for actually doing analysis on the products. So that's a fact that you actually want to pull out. So inside of here, and I'll get into some of the details later, there's a bit of an internal loop that ends up happening where there are multiple agents working together. Some agents just discovering what's available, other agents that are deciding, okay, yes, that's available, but is it relevant? So break those up into separate steps. And then after those agents are done proposing things to each other, criticizing or constraining things, all of what's found, not the information itself, but the kind of information that was found, is also put into another plan. So rather than executing on 1 million files, you do this on a subset of the files to figure out what are the kinds of things that are available here, and also what are the kinds of facts that are available, put that into a plan, and then ask the user, here's what I think is available, here's how I think it correlates with the structured data that I have, does this all look good to you? If you've gotten that far, and I should stop touching the mics, apologies to the AV folks. If the agents have gotten that far and the human has approved of everything, you can finally go through and actually construct the graph. What's happened kind of implicitly along the way here in this multi-agent flow, from the top-level agent, which is purely conversational, helping the user understand what the whole point of this tool set is, to the individual sub-agents that do the work, that have the workflows. The output of all of that, with the graph construction plan for the structured data, the knowledge extraction plan for the unstructured data, putting those things together, you've gone from open-ended problem solving down to what is now basically a plan for how to execute. And now, this knowledge graph construction tool, its only job is take this plan and execute it on however many data files are available. This is the kind of thing that you want to optimize, that you want to have in sort of a batch process, parallelized whenever possible. So having it written in a basically declarative way lets you implement the execution of that however is most optimized for whatever you've got. So this tool here will end up looping over all the rules, both on the structured data side, on the markdown side, and putting everything together. Now, most of this is pretty straightforward. Even inside of this part of the tool, even though this is now just a tool call, even inside of this tool, there's some agents at work. The earlier agents in the middle for the unstructured data that proposed the kinds of information, the kinds of facts, and the kinds of entities that existed that created the extraction plan. To actually execute on that extraction plan, you still need something that's going to go through the text and actually do the work of actually pulling out now the individual people, the individual facts about those people and the products, the reviews, whatever else it finds. One of the things that's important here is that by the time you've gotten to that part and you know the domain, you've figured out exactly what you want to extract, you can optimize a model for actually just doing that last part. You might have started with the top-level agent being ChatGPT's latest 5, 6, whatever they come out with, for open-ended general thinking and conversation. But by the time you get to execution, you don't need a big, expensive model with lots of, also slow model. We're making a bunch of calls out to an API. By the time you get to executing on the plan, you can have local models that have been specialized. In fact, you could take a step back and actually you could insert, if you wanted to, a bit of fine-tuning on the model so that it actually knows the particular terminology that you're trying to extract, so that at the last part, we're actually building the graph, and this could be true in any domain where you're trying to do data import or actually do any kind of data work that is a long process. By the time you're actually doing batch processing, you want that to be as close to like local, the data and the compute all like on the same machine. That's as a general thing, right? This process lets you do that, having started with an open-ended LLM all the way down to the execution plan. The nuance here, the other nuance, I guess I would say, not only for the entity extraction and the fact extraction, specialized tooling and agents for that, there's still the task of, now that you've extracted the people, let's say, and there were people in the CSV files, how do you know these are the same people or not? That ends up being a huge challenge. There are different ways you can take that, take that into account. You already have one advantage where you know that you have people in both the unstructured data that you've extracted and people in the structured data. You can correlate those. Okay, we think we have the same sets of things. How do I know that it's actually the same identity? There, you've got to do your best, taking advantage of the same kinds of similarity tools, either vector similarity for semantic similarity, or even just text similarity. So things like Jacquard distance, what's the other one? The Levenshtein distance, all the different distance measurements that take into account textual differences. So like if ABK appears in all caps on one side, but it's lowercase on the other side, that's a good hint though that it's the same ABK. If you also know from, like, let's say ABK wrote a review, and the review was, in Cambridge where I live, and you also knew that the ABK in your structured data set lives in Cambridge, the more fields and information, the more facts about ABK from the unstructured data correlate with known information on the structured side, and you can do this mechanically. You can figure out that that's probably the same ABK, but rather than merge them into a same node, you'd actually just have a relationship from the extracted ABK to the imported ABK from the CSV file saying, this ABK is probably this other ABK. And you can even assign some certainty score if you wanted to between 0 to 1, the classic thing, like how certain are you that this is the same ABK based on all the matching that you tried to do. At the end of all of this, you should end up with one giant data set that is both structured data, unstructured data, all connected with multiple ways of accessing that data in GraphRag. And with GraphRag, you can still answer questions that are purely based on the text because you have this all inside of a database that can do vector similarity search. You can have vector similarity search and then a little bit of extra context reaching out into the structured data if you wanted to. You could also do pattern matching and aggregation kinds of queries that you might do on the structured side, or start from the structured side and reach into the unstructured side. If you find ABK, you want to find out did ABK have any comments to say about products, you could do that as a pattern match, find the actual original text that you might have scraped from the web, and return all that as a response to the user. This all together ends up being this incredibly powerful model that you can import kind of anything you want to. And you can continue to expand this, covering as much data as you have available, and at each point, capturing how you approach that data into a plan for how to extract that data, both for auditing reasons and for query reasons later on for doing the retrieval, and also so that explaining to the end user who sees some data for the first time, sees some data set, what's even in this data. You can now ask kind of meta questions that in many databases, if you ask a meta question about like, what's this database about, you'd have to go do kind of an analysis, figure out, okay, here's the tables that exist, here's the nodes or relationships that exist. It's probably a movie database or a product database or a logistics network or whatever else it might be. By having captured all of this information into the graph, you have not only the data itself, but the original intent of the data, the whole flow of how the data was created, and you can answer open-ended questions about any level of the graph at that point. Okay. This, again, is the overall system that I just created. This is currently available as of yesterday as a course on deep learning AI. This was just launched yesterday morning at California time. There's a companion project that is a GitHub project. In the deep learning AI version of this, there's basically 8 notebooks that walk through all the essentials of how you build this. It goes through what is Neo4j. We use Google ADK, Google's Agent Development Kit. I explain what Google ADK is, how to use that. And then this whole thing actually gets built notebook by notebook, cell by cell, so you can understand how all this functions on a code level. Being in notebooks isn't the most convenient. It's good for like learning purposes. There's also a new GitHub repository that I've just created where I've taken all of that and like recreated, kind of backported, I guess, in a way, the multi-agent system that has been decomposed into notebooks. It's now being put back together into a single system. So you can give that a try, and also it'll be open source. It's MIT licensed. You can use that as your own work, either for learning about knowledge graphs, learning about multi-agent systems, or building your own stuff if you'd like to on it. Okay. I've got a little bit of extra time, but that's all I've got for today. And I don't know if this kind of stage warrants like having questions. Actually, what I'll do is, if you do have any questions for me, rather than me sitting up here trying to peer out into the darkness and answer questions, I'm happy to chat more about this stuff. I'm going to just be outside for a couple of minutes, and I'm happy to talk more. Thanks.